So hello everybody, sorry for the technical difficulties. Today we're going to be talking about clustering big data and particularly using locality sensitive hashing. Basically locality sensitive hashing is a search algorithm that allows you to do, detect near duplicate or duplicate documents. So imagine if you had a website with thousands of pages and you had identical pages and you wanted to eliminate duplicates or things that were very close to duplicates. We had a use case for a company called Peerbelt where we actually used some of their data where we had to do just that, and we'll talk about that a little later in the talk. Basically what you end up doing is building an index and searching this index to determine if you have duplicate pages or not. And this would allow you to filter out similar documents. Okay, so basically, like there's multiple ways of clustering data. I think K-means clustering algorithms are probably the most common, where you can kind of split up results or documents or what have you into various clusters. So when presented a new document, you have to find the nearest cluster. So you basically can find the documents that are kind of close together, but they're not quite, you're not really getting like the nearest duplicate, you're just basically getting the kind of closest bucketed documents together. I'm just going to skip through some of these. So K-means clustering works pretty well, like for things like anomaly detections. But if you're trying to find, like duplicate documents and trying to build an index, it's not something that's going to work as well as LSH. So there's also no good way to pick an optimal K. You pretty much have to. It's kind of trial and error. I mean, there's ways to test. You don't want too few clusters, and you don't want too many because it'll pretty much skew your results. And every time that you add new documents, you have to kind of rebuild your clusters, which is not very performant. And so it would also force a document to be in a single cluster. So in practice, a document can be similar and in multiple clusters, but you won't really get. If you have a document that's similar in multiple clusters, you may not find it because you're really going to just be targeting one cluster. So LSH works really well in that respect because if you have a document that's kind of listed in a few different places, you would pretty much find all of the duplicates. So all clusters are roughly the same size, and in practice, this is creates these kind of lumpy clusters, and some documents are one of a kind, and those are similar to many others. So again, it's not great. It's not a great solution if you're really trying to search for the nearest duplicates. So in results, it's subject to initial choice of centroids, and the performance is obviously not great. So I mean, you basically have an O and K. Big O notation for the time complexity, so that's definitely not good. The algorithm is not easily adapted to MapReduce, and that can be said for quite a few machine learning algorithms. Like at some point, this scaling the algorithms can be a little difficult, though people have definitely found ways around this. So what are some of the alternatives? Clustering has been picked over quite well due to the combination of interesting math and wide applicability. Two dominant types have emerged: heuristical clustering and partitional clustering, i.e. K-means. And so there's various variations on K-means based on the initial centroid and your choice of K, and other parameters for each iteration. So that depends on your model, basically, that you've chosen. So this gets us to our nearest neighbor search. So based on partitioning the search space, quad trees, KD trees, these are other ways of searching for nearest neighbors, and then enter locality sensitive hashing, which is what we'll primarily be talking about today. So what it allows you to do is to build an index of documents, and then based on hashing and really hashed collisions, you can at least minimize the search space by saying, you know, are these documents similar? I think so because they hash to the same bucket. Let me I've limited the search space that I need to search for my particular candidate document. So it definitely gives you better performance in that way. It uses kind of random hash functions to do this, and we'll talk a little more about that in a few other slides. So basically what happens, as I mentioned, is you end up hashing documents to similar buckets, and so you're trying to determine how similar these things are. And so again, I'll follow up with a little more information about that in other slides. Okay. I just kind of talked about that slide, so I'll just skip to the next slide. So basically, it's very similar to just kind of common search. So what we end up doing is basically creating vectors for the documents that we want to index, and you end up creating very similar, creating a similar vector for the document that you want to search, like the candidate document. So basically, what you end up doing is drawing these kind of random. So what you end up doing is like you're trying to find the documents that are closest together in the plane, and so the real magic is choosing your hashing functions, and that'll obviously make a difference for, you know, depending. So the hashing function that you use and the distance measurements that you would use would be based on the kind of documents that you're trying to process. So basically, what happens is once you have processed your documents, you want to add them to buckets. The buckets are also kind of split up into bands, and so by splitting up the documents into buckets, you are pretty much allowing yourself. You would allow yourself to minimize the search space once you're ready to search and you have a candidate document. So again, that also helps with performance because you are not searching for every document that you have. You're kind of targeting a certain bucket because a document is hashed to that bucket. Okay, so some brief history of LSH. So the origins were at Stanford in 1998. And so it's actually being continued. It's continued research in many universities, including Stanford, MIT, Rutgers, Cornell, and as well as in industry in Intel, Microsoft, and Google. There is even some, at least one paper. I can't remember the authors at this point, but I could find it if anybody was interested, where researchers have created a more parallelized version of LSH for trying to get better scale. So minhash is a common algorithm for basically choosing the hashing function, like basically for choosing the hashing functions that you're going to use. So what you end up doing is you take your document and you split it into shingles. You can shingle your document either by character or by word. I think we found that by character works quite well, especially if you have pretty small documents. If you have really large documents, I think by word is more performant and works quite well. And here are some examples of what shingles look like. So they're basically, you know, just you can say I need n number of characters in my shingle, and so you would a string like Mary Hatta would be split up into shingles that look like this. So then min-hash works by you basically compute a hash for every shingle, and then you take the minimum hash for that. So this acts almost like random sampling, and then you repeat the steps for at least 200 min-hash values. And so this actually, like I said, works pretty much like random sampling. So it works out quite well. So what you end up having is 200 integers or 200 hashes that represent a random selection of shingles. And the property of min-hashes, if the min-hashes for two documents are the same, the shingles are likely to be the same. And this is kind of where, this whole idea of bucketing your documents that you are indexing comes in. If the shingles for two docs are the same, the docs themselves are likely to be the same. So this is one caveat. Min-hash is specific to a particular similarity measure called Jacquard similarity. And this really depends on, so there's other hash families of, that exist for other similarity measures, and it really depends on, the kind of documents that you're going to be searching. Like, for example, if you were trying to find duplicate images, you would obviously want to use a different similarity measure because the metric space may be different. So the property of your documents makes a big difference. But for strings, min-hash and Jacquard similarity work quite well. So if all the min-hashes match, it implies a strong similarity between documents. To catch most cases with weaker similarity, don't compare all min-hashes at once, compare them in bands. So that was what I mentioned earlier, where your buckets are split up into bands. And so the beauty of this is that you only need to match in one band. You don't have to match it. Like if you have 10 bands, you only need to match in one. So this, again, is where you get better performance because you're minimizing the search space and you don't have to search all your documents. Unlike, if you were using k-means clustering, for example, you wouldn't need to search for everything just to try to get, see if your candidate document has a similar document already indexed. So sometimes one band will reject a pair and another band will consider it, and sometimes you might match in every band. So pick the number of min-hashes, the number of bands, and the number of rows per band to balance false positive and negatives. And so these are the parameters that you use to tune your LSH implementation, and it really depends on what you're willing to tolerate and what you're really looking for. So false positives, you need to examine more pairs that are not really similar, more processing resources, more time, etc. False negatives, failed to examine pairs that were similar, didn't find all similar results, but got done faster. So again, this is just kind of a classic trade-off with just search algorithms in general. Like this whole debate against precision and recall. Like what are you really looking for? Like what do you actually want to accomplish from your LSH implementation? So in summary, you mine the data and place members into hash buckets, which is basically building your index. When you need to find a match, you hash it. So you basically you end up creating a vector for your candidate document, just as you did for your documents that you index, which is very classic search stuff. And so you hash it, and then you have you try to detect the possible nearest neighbors, and which will be in the number of buckets. And the algorithm performance is ON, which is obviously much better than what we noted your typical k-means clustering algorithm would be. Okay, so we have a demo, and I need to kind of get to a different screen. Are there any questions? I might have gone through that a bit quick.
Teresa?
Yep.
Someone asked, what about K&N instead of LSH?
Sorry, say that again. What about what?
What about K&N instead of LSH?
I'm honestly not familiar with K&N, so I can't really make a great comparison. I'm more familiar with like k-means, so that's probably where I could draw the best conclusions. Mm-hmm. So I'm not familiar with that algorithm.
Okay, you know, I'll leave as a question too, when we get Jay or maybe later on the LinkedIn group,
Okay.
we can have Jay address that question, so I will write that down and we'll address that on the LinkedIn group discussion.
Okay, that sounds good. Okay, are there any other questions, or I'll move on to our demo?
No, please proceed.
Okay, so OpenLSH is a implementation of LSH that Jay started, and I soon after started helping out with. So he proposed at a meetup on the topic about creating a nice framework for allowing people to do this, and open source, of course. And I was really interested in kind of web scale search algorithms, period. And this was a very interesting algorithm, so that's how we got started. And our first use case that we tried last summer was using tweets. I mean, so, you know, we have, like, Twitter has a really nice API. They offer a sample of their Firehose, which is all their kind of public tweets. And they're very short strings, and they would lend themselves quite well to a test use case for LSH. And so Jay built this really cool interface. And so I'm already kind of logged in. Basically, you have to log in via, in order to use this, you would log in just kind of clicking a few links to log in via to Gmail and to Twitter, and we can basically run this to get some tweets, and it'll analyze it and tell us the duplicates. So these are results from a previous run, so I'm going to run this again. And what we found was that, you know, because we're shingling by character, even if the tweets are in a different language, we still can detect duplicates, which was really, really cool. So we're just going to let this run. So what it's doing now is just fetching tweets, and then once we fetch the tweets, we'll calculate the LSH buckets, and then we can determine in our block of tweets that we received how many duplicates or similar tweets we have. So it'll take a few minutes. Just it should be loading soon. There we go. Okay, so on the right-hand side, you'll see the similar and identical tweets. So identical tweets are obviously usually retweets. So as you can see here, we found tweets that were 64% similar, and this key indicates where the tweet differed, like the two tweets that we compared, where they differed. And this is the Jacquard similarity metrics, which is basically like a ratio. It's all basically comparing sets of shingles, and it gives you a ratio of how similar your sets were. And your sets would just be like sets of shingles for every document that you've processed. And so as you can see, it works quite well. Tweets are a really good use case. And like I said, as you notice, even if the tweets are in a different language, we're able to still identify whether we had a similarity of pairs or if we had, identical matches. And so this is available to use. The OpenLSH Git repo is also up, and I'll talk a little bit about that. Sure. Okay, so I had mentioned earlier in the beginning of the of our talk that there's a company, Peerbelt, that basically they're kind of working to almost eliminate the need for bookmarks. So if you search for something and you're running the Peerbelt application, you can get a kind of customized version of what you search for, and it actually works quite well. But one of the problems that Peerbolt had was that they had indexes of lots of HTML pages, and they had tons of duplicates, and so that's obviously an issue for storage. It makes searching things not as performant because you're searching over duplicate documents. And so this is an example of what the matrix that gets built or the index looks like. And so as you can see, the matrix can actually be quite sparse. And so these little red dots are where we had matches, and these are hashes for the actual documents. Sorry, I'll go back to that. And these here are the hashes for the actual documents. So in our implementation, we had to have a pretty large number of buckets. So this is because of you're indexing very large number of documents. You are going to need this, obviously. So most of the buckets are going to be empty. As I mentioned before in that example, when I showed you the image of the example of the Peerbolt matrix, it's very sparse, so most of the buckets are going to be empty, and you don't want the empty buckets to take up any space in the database because obviously that's just not efficient in terms of storage. Some buckets will have lots of documents in them, and you obviously will need a way to locate them all. To find the document similar to a given document, bucketize the document, then find other documents, and basically that's just part of the LSH implementation. So as I mentioned, OpenLSH was started to provide a framework for LSH. So there's other implementations there, but usually people have to roll their own. And what we wanted to do is, in the beginning, we wanted to factor out the database. We didn't want you to have to really worry about what database do I choose. How do I get this model, in these matrices built in various different databases. So we use Google App Engine, which not only provides excellent storage, but it also provides a means of testing and scaling without having to set up a lot of infrastructure on your own. We created a virtualized interface to make it work in Cassandra. So the Cassandra use case was actually built out of using the Peerbolt data, and that was kind of a requirement that they had. And so we were pretty lucky to be able to use their data so that we could basically start implementing a version of OpenLSH that would scale. And so that scaling was done by, Jay did a lot of good work over the fall by basically taking our kind of prototype LSH implementation and scaling it to use Google MapReduce and Google App Engine. And then, as I said, we then ported that to run in batch mode on Cassandra, and so that worked quite well as well. And all of this is implemented. All of this is implemented in our OpenLSH repo. So we're still looking for really interesting use cases. As we said, like the near duplication was covered with Peerbolt's data, and even our test use case of using tweets. So stocks that move independent of the herd, filtering unique stories from the news. These are other, kind of potential use cases, but I suspect that there are many more. So contact us to discuss, because we definitely like to work with other people that maybe have some cool ideas. So if you're interested in learning more about OpenLSH, you can go to the DataThinks website. There are links to the GitHub repo there, as well as the data set, and you can try out that demo tweet application that I just showed you. So it's very easy to set up if you want to run it on Google App Engine, and then you can adapt this to the environment and your particular needs and the documents that you want to process. Oops. Okay, thank you. That's the end of our talk.
Thanks, Teresa. Yeah, and sorry, I've been going back and forth here with Jay, and then unfortunately the technical difficulties prevented him from coming on. But at the moment, we'll do some questions, and we'll put them out there, and if maybe they're more appropriate for Jay, then we'll just, as I mentioned, we'll put them on the LinkedIn group and have them discuss there. But a couple of the things were, Someone had asked, how performant is the hashing function?
Well, it depends on the hashing function, right? So, like for the prototype that we built, I think we just used whatever Python's default hashing function was, and then basically iterating and creating variants of that. I think it depends on. I think that there are some fast hashing functions. It really kind of depends on. I mean, there's many different hash functions, so it depends on what you're using. I think that the bottleneck, I don't think that the real bottleneck was so much in the hashing. I mean, sometimes the shingling can take a while. Especially, let's say, if you had a very large document and you were shingling by characters, I mean, that can take a while, especially if you have any pre-processing steps, like there's things like removing white space and stuff like that to hopefully get better results. I think that Jay did recorded some metrics with our implementation, specifically using the Google App Engine's MapReduce API. So he might be able to tell you a little more about specifics about the hashing algorithm that we're using.
Okay, I made a note again for the LinkedIn group to see if Jay can share some of his metrics.
Okay.
We're getting a lot of questions here. Let me get them organized. Someone had asked, so this is only for NLP or text applications, or are there other areas other than NLP or text that you can see it being used?
Oh, definitely not. I mean, so one of the more common use cases, I think, is for detecting duplicate images. And so, like I said, your metrics space that you use will pretty much be determined on, and the metrics for detecting similarity or distance between two documents will be determined based on what kind of documents you're processing. I think text is also a common one, but I know that images are common, and I think that that's definitely, we wouldn't use like something like Jacquard and similarity and min hashing for that.
Okay. What kind of text pre-processing steps have to be done for OpenLSH?
Well, so there are things that they suggest in some texts that I've read, like eliminating white space and things like that. I mean, it really depends on where the data is coming from. And this is not just for LSH. I think, well, that particular, the white space is maybe, and maybe doing some normalization with, removing. Maybe you might want to remove punctuation, but that could skew the results. But in general, I think it really depends on just where your data is coming from. And that's more of a kind of just a common, platform development, like data processing, processing step. And I think it really depends on where the data is coming from.
Have you used a package to do the text preprocessing?
Well, no. So I think that for PeerBelt, the only thing that was used when we were testing that data was we used Beautiful Soup for parsing HTML and maybe cleaning some like script tags and things like that we didn't really need as part of like the actual document. For the prototype that was built last summer, no. It was very basic things that we need to do, like removing kind of erroneous white space. That was all stuff that you can do very easily in Python. Again, I guess it really depends on your data needs. Like if you were scraping data, let's say, from the web, that data can be quite dirty, and you're most likely going to have to add your own steps to make sure that it's as clean as possible. Because any additional text or tags or anything, especially if it's HTML, for example, that will have an effect on, that's going to now be a part of your index. So that's going to affect the quality of your results.
Mm-hmm. Okay. I was thinking there was an open source package that I've used sometimes, and I can't remember the name of it. I thought it was Tika. but as if someone in the group representative that sounds familiar, if you think of it, yeah. Apache Tika is something I've used.
I think I've heard of that. I haven't used it, but I think I've heard of that. Yeah, I'm sure that there are, it depends on the use case, but like I said, I'm sure that there are packages, but if you have some very specific needs, in my experience, I've ended up having to kind of roll my own.
Sure.
Because it's, usually it's very specific to the data set that you're processing.
Does OpenLSH support Euclidean distance?
It doesn't, but it can if someone wants to implement it. That's a very common metric space, and so it would be pretty awesome if somebody wanted to help write that, or I guess we could write it. It doesn't, but that is a very common metric space for LSH and search in general.
Okay, well that's great. If someone is interested, again, we'll have your presentation up on the website, and your contact info is here. Really, as Teresa mentioned, if someone wants to get involved or work with Jay or Teresa to extend or enhance these algorithms or this application, I'm sure they'd be open to talking with you. A few more questions. Comment was one of the questions was, is this only for NLP or text, or can you use it for other things? And I think you had mentioned images, and someone made the comment, so far for images, the best is convolutional neural network. Wondering how LSH rates against convolutional neural networks, if anybody knows, or if you know.
Yeah, I don't know. I've never used that. So it would be interesting to see. Like the implementation of LSH, I think, also makes a difference. So as I mentioned, we, in order to scale, which is a common way of trying to scale this algorithm, is to implement it using MapReduce. Because of the hashing the hashing bit, which is so important to it, it actually lends itself well to using MapReduce, because you can use the partitioning function, which is basically a hashing function, to do the bucketing for you. So it works quite well. But I'm sure that, like I mentioned earlier, there is a paper which I could post it. I'll have to find it, where some researchers have done a parallelized variant of this, and they're supposedly have gotten very good results. So again, I'm not sure, how it would compare with other algorithms for detecting duplicate images, but it would be kind of an interesting use case to see if you could get better or comparable results.
Okay. Another question. How can I make use of LSH to get some K clusters of the data points instead of a query point? Maybe that needs some clarification.
I guess I was going to say, what's the use case? Why would we? Because the bucketing basically is kind of clustering similar documents together, so to speak. But it's a different. I think it's basically a different way of trying to find similar items. Because usually with k-means, you have data that you don't really know, right? So you're trying to see if there's any patterns or similarities, and it doesn't really lend itself well to kind of on-demand searching. It's just not used for that. So in this case, though we are kind of clustering data, I think this is a better use case if you're trying to find actual similar documents. So I don't know if that answered the question. The question wasn't completely clear.
Okay. No, I think that was a good answer. This, going back to NLP and text questions, also